So, hello everyone. It's my great pleasure to welcome all of you to today's international online seminar on interval methods in control engineering. And it's my great pleasure to have today with us a colleague from China, Mingshuai Chen, who is currently an assistant professor and leading a formal verification group uh, in Hangzhou. And yeah, before that, he especially also worked in Germany as a postdoctoral researcher at the University of Aachen. And yeah, he also had lots of collaborations with one of our colleagues here in Oldenburg, with Martin Frenzler. And we're now looking forward to your presentation on derivative-agnostic inference of nonlinear hybrid systems. The floor is yours.
Thank you, Andres. Many thanks for the invitation, and it's really my great honor to be able to give a talk here at the seminar. So because I have to write somewhere else, I will turn off the video during the talk, and I will reopen it during the questions session. Yeah, so this is a talk which is not really close to interval methods, but it does have some connection with control engineering. And the talk is about how to infer a hybrid system from some observations, let's say. And this is a joint work with my students at Zhejiang University, as well as colleagues from Chinese Academy of Sciences, Beijing Institute of Control Engineering, as well as Peking University. Good. So this is not really about interval methods, but I will try to give you a story which builds upon the well-known cyber-physical systems. It is a model, or let's say it's a type of system which has an open interconnected form of embedded systems. And it usually integrates the capabilities of computing, communication, and control. For example, we have some automobiles, spacecrafts, high-speed railway systems, etc. And there, in this type of systems, we have some, let's say, computer programs to control the physical plant, which evolves continuously over time. And to model such type of systems, a well-known mathematical or formal model is the hybrid systems, where basically, let's say, if you look at hybrid systems from a macro view, then you will have a set of locations, or we also call this modes. And then we have some usual discrete jumps between those locations. And within each location, instead of the traditional, let's say, DFA, and we usually have some continuously evolving dynamics within the mode. For example, you can model the velocity of a train within a certain mode. And if you look at a micro view, then this actually models a closed loop feedback system where we have a physical plant to control, and we also have a control program, which, let's say, periodically senses the state of the physical plant, and then do some computation, and eventually actuates some control commands back to the physical plant. And the key of this type of system is really the interaction of the discrete jumps with the continuously evolving dynamics. And such dynamics is usually modeled by the ordinary differential equations, or ODEs for short. Good. And now, based on this general picture of cyber-physical systems, the question is, how do we really design and develop such kind of systems? And here I give a typical pipeline that is used in practice. Basically, we start from some formal model, let's say a formal model like this, which is a hybrid automaton. And there we have some ordinary differential equations with each of those locations. And then we also have some discrete jumps between those locations. And starting from such formal model, we will continuously or consecutively refine this abstract model into some real implementation of a system. And one such model is called the Simulink model, or some other similar types of models, where basically you have a graphical model which consists of different types of blocks, and then you can simulate such a model and get some testing or simulation results. And next step from this model would be to translate it into some executable computer program. And this constitutes the software system of the real cyber-physical system. Yeah, this is a typical perfect pipeline for developing such a cyber-physical system. But the truth is, this is not always the case, because sometimes you may have some black box system, or you don't have a built from scratch formal model at hand. And in this context, people propose a reverse direction as a new problem called hybrid system identification, which basically asks to infer a hybrid system model from some external observations of a real cyber-physical system. And we call this hybrid system identification or model learning in a more general context. Okay, so this would be the whole problem this talk is focusing on. And in order to solve such a problem, there's a typical pipeline in the literature. Basically, we start from some target hybrid automaton, which is a typical model for hybrid system. And this is a black box system, so we can only simulate or sample it. For example, we can get a set of discrete time traces from such a system by running it or by sampling. And we call such traces the learning data D. And from such learning data, the goal is to learn or infer another hybrid automaton. I will write it as bar of H, whose behavior closely approximates the target hybrid automaton. This is the problem. And we call it hybrid automata inference in the typical automata terminology. And among all of different pipelines, there's a very commonly used one. And I plotted here. Basically, it consists of 5 steps. The first step is to do the trace segmentation. Basically, we take some trace, which is a discrete time-stamped data, and you try to partition it into different segments. For example, this one is a segment, this one is a segment. And we hope to partition it in a way such that every single segment is produced by one of the dynamics from the modes. And after doing the partitioning, we actually have a set of different segments, like on the picture. And the next step is to do the clustering, which basically means we group those different segments into different clusters. And the hope is that every cluster corresponds to a specific mode in the original hybrid automaton. Here I write a question mark because there are different ways to do so. And after we have such different clusters, we can learn or characterize the flow dynamics within each mode. Now, for example, these 2 segments may be produced by location F2. Then we can learn a ordinary differential equation or some other type of dynamics which produce such 2 segments. And in the meantime, we can also learn some guard. And guard in the model basically means when you can trigger such a discrete jump from modes to modes. And when after we have such kind of guards, we can learn reset. And reset basically means after taking such a discrete transition, what kind of update I can do to my system state. This is the general picture. And many existing approaches in the literature actually follow such a pipeline. And here I give a far from complete landscape of such approaches. Most of them are very recent works in the community. And as you see in the table, some of them can only infer a subset of hybrid systems. For example, switch systems, which is basically a switching with very simple logic between different modes. And of course, some can generate general hybrid automata. But some of them focus on polynomial order differential equations. right? And some other can only generate linear dynamics. Well, they differ in many dimensions. And also I list whether the approach can produce high order dynamics. Many of them cannot. This basically means they can only generate first order ODEs. And some approach can allow reset learning. Some others can allow input learning. And our approach on top of this landscape actually complements with a new inference framework called Dainarx. And this Dainarx stands for Derivative-Agnostic Inference of Hybrid Automata using a model so-called NARX, so NARX. And I will introduce what a NARX model is later, but the message is that our approach enables the learning of a general hybrid automaton with nonlinear dynamics, with high order dynamics, with linear reset, and with external inputs. And this is, to the best of our knowledge, the first approach that can actually allow such a permissive form of hybrid systems learning. And to give you a general overview of the framework here, I have a plot which actually instantiates the typical pipeline I've just introduced. By this picture, I will not dive into technical details, but the key message that I want to show through this picture is that we use the technique of NARX model fitting as a common ingredient to different steps of the pipeline. For example, we use this NARX model fitting for segmentation, for clustering, for mode characterization, and also for reset learning. The only different step is the guard learning, where we use classical SVM technique I will introduce later. Next, I will give you an example on what kind of systems we can learn and what is the key difference from the other approaches. And this example is a motor, a PID-controlled permanent magnet synchronous motor. It looks like this. So it has a magnet at the center of the motor, and the goal is to control the rotation of such a motor using a PID controller. And here, this is the commonly used model in control. Basically, theta here is the angle of the rotation of the motor, and V is the voltage of the controller. But this is a very commonly used physical device in many areas, for example, in UAVs, in mechanical arms, robotics. And suppose now we have such a simple system which operates in 4 different phases. And all the different phases are for different control targets. For example, this mode, the control objective is to try to maintain such a motor at a certain angle. So the angle here is modeled by this reference angle 1.1. And in the other modes, we want to maintain the motor at a different reference angle, 0.1, and etc. And the dynamics within every of such modes follows a similar one, which is this equation. You see the reference angle here. And this equation, the notation is as follows. So theta 4 is the 4th order derivative of the angle with respect to time. Okay, and so it's really a high order ordinary differential equation. And suppose we don't actually have such a dynamic model, but we want to learn from data. This is the goal, right? And now we can start from some given discrete time data. Suppose this is a true trajectory of a continuous system. And I will first mark on top of this picture, I will mark the mode switching point, the black dot. Basically, such a black dot means the system will jump from one mode to another. Okay, so a discrete jump happens at this point. And this is the true mode switching point. And now suppose we have some sampled data, which I use this empty circle to denote all these different samples. And suppose we are lucky also to sample the real mode switching point as part of our learning data. And now the goal is actually to learn a hybrid automaton which will produce trajectories like this, right? Now the first is to do the segmentation, basically to segment such a trajectory into different partitionings. And before I show how Dainarx will do, I will first show you what an existing approach will do. Basically, I take one of the existing approach, Famos. And this approach is a very typical derivative-based approach. Basically, how it identifies a mode switching point, or I call it CP change point here. It's based on the derivatives, or more precisely, it's based on the change of derivatives. For example, look at this point. So the Famos approach will tell you this is a mode switching point because it observes a very drastic change in the first order derivative, right? And it also tells you this is a mode switching point because it also features a drastic change in derivatives. So this is not surprising how it can do so because it has a threshold, let's say gamma. Whenever the derivative change is beyond such a threshold gamma, it will identify such a point as a mode switching point. But apparently this is a fake mode switching point or a spurious one, because we know that all the black dots are the true mode switching points, even though some of them are not obvious because it doesn't feature a drastic derivative change, but still it's a mode switching point. Such a method can identify spurious mode switching point. It can also miss some true mode switching point. And in contrast, our approach can give you, in this example, the precise mode switching points, which are marked by the green circles. And I will tell you later how we can do so. And by having such change points, we can actually do the segmentation naively by partitioning the time domain into different segments, which is indicated by the dashed line here. And now, after having such partitionings, the next step is to group different segments into different clusters, right? And here I use color to indicate the true clustering, because this trace and this trace, they are marked both green because they are actually from the same mode. They are generated by the same ordinary differential equations. But again, I will contrast our approach with existing ones, which is trace similarity-based clustering. And basically, the idea is to take two traces and to compute a certain difference between the two traces. If they are below some threshold again, they will be treated as this as from the same mode. For example, if you take G1 and G2, you will see that these two traces look very similar in a certain measure, right? And such a trace similarity-based clustering method will group these two traces actually into the same cluster because they look very similar. But the point is, similar traces do not imply same mode dynamics, and neither vice versa, right? For example, G1 and G5, they don't look similar, but they are actually from the same mode. And in contrast to a similarity-based approach, our approach actually works in a different mechanism. Instead of working on the trace feature space, let's say, we lift from such a perspective to the flow dynamics feature space, and we say two traces belong to the same mode if and only if their corresponding flow dynamics look similar. So this actually gives us the possibility to group F1 and F3 into the same cluster, and F2 will be clustered into a different mode. all of these are based on a technique called NARX model fitting. So next, I will introduce such a model. But the general idea, I think, is already well delivered. Then, what is a NARX model? It's let's say a case NARX model, case order NARX model is nothing but a difference equation. Okay, it's a high order difference equation written this way, where this x of tau is the let's say current system state x on time tau is a vector, and then the such a vector is based on k recent histories of the same system state, right? And then it also depends on the current input from external and this can be a linear function fq. Q here basically means the mode q. This is potentially linear, nonlinear. And in order to represent such a model in a more precise or standard way, we do a rewritten of such a model. And this rewritten is also not complicated. Basically, we take all the nonlinear terms and take the coefficients of such nonlinear terms. We organize them in such as a linear combination of nonlinear terms. And we also take the linear terms outside and combine them together. And here, this is the element-wise matrix production, and this is normal matrix multiplication. By doing such a rewriting, now we can actually represent such a model using a coefficient matrix like this. Basically, we take all the AIs and we arrange them into a matrix like this. We do the same for all the coefficients b and bk plus 1 and c. We group them into the same big matrix, and we call such a matrix the coefficient matrix. And now you can actually use such a matrix plus the nonlinear terms to represent a NARX model. And this is a notation like this. So we have a NARX model N is represented by a coefficient matrix and some nonlinear terms. And when such coefficients are unknown, so basically they are some unknown parameters, then we call such a model a template NARX model. We can also instantiate a template by, let's say, finding a specific parameter coefficient matrix, and we call this the instance of the template under such a specific parameters. And we use this angle bracket notation to stamp the set of all instances of a certain template. That's all the mathematics. And now, as I said, NARX model fitting is the common key technique we use throughout our framework. Now I will show you what a NARX model fitting is. Basically, the task is that given a template model and given a set of traces, our task is to find a coefficient matrix such that our instantiation under such a coefficient matrix actually fits the set of traces. And by fitting a set of traces, I mean such a set of traces can actually be produced or generated by the so instantiated NARX model. And we write this as the notion of fitting, okay? This basically means our instantiate model fits the set of traces. In a more intuitive way, suppose we have a template NARX model like this, where we have two nonlinear terms, okay? And we have some unknown coefficients to fit. And we are also given some traces, and for the sake of simplicity, I will use only one trace through the explanation, which is this trace. And we actually are given some discrete sample points, right? Like this. And how do we do the fitting? We do it using the well-known linear list squares method. How it works is as follows. So we maintain two matrices, one called O and the other called D. And the O matrices is nothing but to record the observed value of a certain variable. For example, we can arrange x4 in the first column of such a matrix. And then corresponding to x4, we have a row vector in the data matrix, which can be used to plug in to this NARX model. Basically, you can substitute all the data into such a template model, right? And similarly, we have x3, which corresponds to the second row of this data matrix. And we also have x2, which corresponds to the first row of this matrix. And apparently, if you substitute every row into this model, you will have a constraint about A, B, and C, right? You will, if you have concrete values of these parameters, you will get the value on the right-hand side. And our fitting objective is that such a value is close to our observed value, right? So the difference between these two should be as small as possible. And this is the linear list squares methods, how it works. Basically, we want to minimize the distance between the observed value and the value after plugging data D into our NARX model. And we want to minimize this. And if we are lucky, we get an objective of 0. This simply means we actually found a specific NARX model which perfectly fits this the trace G. And if this value is larger than 0, then we don't have such a model. This is the math behind that. Yes, good. Now we can use such a simple fitting technique to solve almost all the sub-steps of our inference task. How do we do this? We start from the very beginning, which is trace segmentation, right? And this is what we have. We have a trace, we have some different sample points, and also we have the true mode switching points. This is the true mode switching points, but we need to identify such mode switching points. How do we do this? We maintain a sliding window. Let's say this is a sliding window from the left to the right, and the length of such a window or size is W. And now we look at this window, we look at the trace within such a window. And the task now is to check whether there exists a NARX model which fits such a trace segment within the time window. If there does exist such a model, that means this whole trace segment might be generated by a single ordinary differential equation from a single mode, right? Because the basic assumption is that whenever we switch from one mode to another, we will switch from one dynamics to a different dynamics. So what we can do next is to slide the window a little bit to the right by incorporating one more sample point like this. And now we do again the check whether there exists a NARX model which fits the trace segment within this window. If yes, again, we can confirm that there is a single dynamics which well fits the data. And we could keep doing so until a special situation occurs, which is this one. Because if this is a true mode switching point, that means this part of segment is actually generated by a new mode dynamics. And because the new mode dynamics is assumed to be different from the previous mode, that will make the same NARX model incapable or insufficient anymore. Because in order to fit this trace, you need at least two different NARX models. So we observe that there does not exist a single NARX model which can fit the data. Now we can label this mode as a potential mode switching point or change point. This is the way we identify change point. And we keep doing so. Starting from this step, we can do a jump, a sliding window jump, because we are sure that if we move another sample point in to the right, we still cannot fit this trace because we have a mode switching point within it. And that's why we can, in this case, we can do a window skip. We directly skip to the next window. And then within that window, we keep doing the same trick until we find the new switching point here. We do the same until we can find all the mode switching points. This gives us a segmentation of the trace, right? And this is the idea. And after we have the segmentation, the next step is to group different partitionings or different trace segments into different clusters. So let me first label the traces again using colors. How can we detect, or how can we conclude that G1 and G5 are from the same mode? This is again, this again can be done by NARX model fitting, because we can conclude that there exists a certain NARX model from our template, which fits both of these two traces. Okay, and this tells us there is a mode where the mode dynamics can produce both G1 and G5, even though they look rather different. And for the other three segments, they belong to single individual modes, because none of them can be produced by the same mode dynamics. And by such a simple check, we can actually conclude with the clustering of the segments. The next step would be to learn a specific NARX model or dynamics from the cluster of segments. How do we do this? We simply apply again the NARX model fitting technique to find a specific NARX model that actually fits both G1 and G5, and we do the same for the other trace segments. And this gives us 4 different modes in our example. Good. Now the next would be to learn guard. Basically, it means to learn an expression or a guard, which characterizes when you can jump from one mode to another. For example, in this picture, we have 3 modes: Q, Q prime, and Q double prime. And now we already have trace segments within this mode. We also have trace segments within the next neighboring mode. And now the thing is to try to learn the decision boundary, which tells you when you can jump from this to this. And we do this by SVM, so a classical binary classification problem, by providing some positive and negative sample points. Basically, we use these 2 points, which actually trigger the discrete change of modes as some positive points, and all the rest of the points, which do not actually jump from Q to Q prime, will be treated as negative points. And this is the formal definition of these 2 types of points. And by having this positive and negative points, we can learn a decision boundary, a possibly non-linear decision boundary, which separates these 2 types of points. And this gives us an SVM-based guard learning approach. This is not new. Many of existing approaches use the same technique. And then the final step would be to learn the reset. And again, the reset means after taking the transition, how you can update your system state. And actually not only your system state, but also the higher order derivatives in your system, because we cater for high order dynamics. So what really happens at a mode switching point is that you take the current vector of state, which has both the current state and also the first order derivative, blah, 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 until the k-1 order derivative. This encodes all the information of the current state. And then whenever we trigger a discrete jump, mathematically what it does is to use a linear transformation, which transforms such a vector into a new version of such a vector. And such a multiplication is what reset does, right? It updates the current system vector. But the problem for this is that all the higher order derivatives, all such information are not in our learning data, not in our D, because our learning data only has trajectories of the zeroth order derivative, let's say the current system state. And because of the absence of such information, we cannot learn such a transformation matrix directly. How do we do this then? We use NARX model fitting again. The general idea is that instead of learning such a matrix, we learn a mapping which takes the history, the K history of our trajectory, and predicts the K future states of our system. And how do we represent such a transformation? We use NARX models. And it works as follows. So we take this part of the trajectory or the trace, and we fit a NARX model N1. And this model basically gives us the possibility to predict this point using K recent histories. Okay. And we do the same for the next point. Basically, we fit another NARX model N2, and this gives us the power to predict this point using, again, K recent histories. We do the same until we have K different NARX models, and this K different NARX models actually encodes the power of such a mapping. Whenever it is provided with some history points, it has the power to predict or update the future states, let's say. And using such K NARX models, we actually has a different alternative representation of our reset. So from the left to the right, this is not always complete or correct. We're not sure. This is only a kind of approximation. But we do have a conjecture that in the linear case, when the sampling points are dense enough, we can actually reconstruct this transformation matrix T using NARX models. But in the nonlinear case, things can be rather complicated. Good. All the technical parts are done. So I've basically introduced all the algorithms we use to learn hybrid systems. And we have implemented all the algorithms into a tool called the same name, Dainarx. And we have open sourced it on GitHub. You can also scan the QR code on the right-hand side to play a bit the code. But warning that this is still under construction, so don't be surprised if you are catched by some weird bugs. And our tool basically works in an end-to-end fashion. So if you have a real hybrid automaton system and you have some sampled traces from this system, you throw the traces into our tool together with the template, a NARX template, then our tool is capable to provide you with the inferred hybrid automaton in such a form where all the mode dynamics are represented by NARX models. So they are not really continuous differential dynamics, but they are, let's say, a discretized version of such dynamics. As you can see, it closely approximates the behavior of the real system because, like if you can see here, that the generated trace is really close to the authentic trace, let's say. And we call this a high trace fidelity. Yes. In order to evaluate the effectiveness of our tool, we did a lot of experiments. I will first report the experiments on linear hybrid systems where we collected, I think, 26 different benchmarks. They all have different features. For example, this Q is the number of modes. We have complicated systems where we have 8 modes, and this X is the number of output variables of the system, and K is the order of the dynamics. And we compare our tool Dainarx with 2 baselines. One called LearnHA. It's a recent ATVA paper, which is dedicated to learning polynomial dynamics of general hybrid systems. Another approach called FAMOS, as I introduced, this is dedicated to learning linear hybrid systems. And in terms of metrics, we do 3 different metrics. The first one, this actually measures how close the identified change points are from the real mode switching points. So the smaller the value is, the better. And the other 2 metrics are to measure how close the learned automata is to the target automata by comparing the traces generated by the 2 models. And again, the smaller the better. This is the maximal distance between the pointwise distance between the trace segments, and this is the average distance. So 3 key messages for the experiments. The first one is on applicability. Basically, as you can see from the table, that our approach suffices to infer the hybrid automaton for all the 18 benchmarks. This is not the case for the other 2 baselines. For example, Learn HA cannot handle systems with higher order dynamics. And FAMOS cannot handle systems with let's say, impulse resets or some complicated behaviors. But Dainarx can handle all of them. Sorry, give me a sec. Yes. Another message on the segmentation accuracy. As you see from the blue box, that Dainarx actually achieves the highest accuracy or the tied highest accuracy in detecting mode switching in all the 18 benchmarks. So we always get the smallest value, which is the closest to the real mode switching point. Another message is from the green box. It tells us that Dainarx attains highest trace fidelity across 17 out of 18 benchmarks. The only exception is this one, where we use where we have a comparable, let's say, a trace fidelity with Learn HA. But overall, I think this table clearly demonstrates the advantage of Dainarx. And this picture gives you a bit of more intuition on the trace fidelity. For example, on the left-hand picture, this is for the complex tag system, where, as you can see, the red one is the learned traces by Dainarx. It closely approximates the black trace. And in this example, FAMOS gives a second best approximation, and Learn HA gives, let's say, the worst in this case. But things are different for another example called Bach converter. There, Dainarx still gives the perfect trace, perfect approximation. But in this case, Learn HA performs better, but FAMOS gives worse trace fidelity in this case. Now we move to the nonlinear experiments. In this case, we don't compare Dainarx with any of the baselines because, so first of all, FAMOS can only handle linear case. And then for Learn HA, even though it claims that it handles nonlinear dynamics, but we find the implementation itself is not so stable for the benchmarks in our case. So we couldn't achieve reasonable experiments with that implementation. That's why we only evaluate our own tool, Dainarx, in this setting. And the message for this evaluation is that Dainarx is effective in learning high-order nonlinear systems even beyond polynomials, because as you can see here, we have some trigonometric flow dynamics in guards, and we can still learn a tight approximation to such a system. But of course, why we can learn such a type of dynamics is because we can provide templates like the trigonometric function as the nonlinear terms. But this is a common trick for all the template-based approaches, of course. Good. And then instead of apart from effectiveness, we also evaluate the efficiency of different baselines. And we use this big table to report how fast we can learn a hybrid automaton and how does it compare to other baselines. On the right-hand side, this is the total time used in seconds to learn a hybrid automaton. And we also report 3 steps: segmentation, clustering, and guard learning. These are the most time-consuming steps in all the benchmarks, in all the different baselines. The other tools are, the other steps in the pipeline are negligibly small. Okay, good. The message for this table, first, segmentation dominates the time of trace similarity-based methods, because as you can see here, that similarity-based approach really needs to compute the similarity between different traces extensively throughout the clustering phase. That's why it needs so much time that this proportion of time actually dominates the whole the running time of the tool. In contrast, Dainarx doesn't really need to compute similarity, so this part is rather quick in Dainarx. And speaking of total time, Dainarx is 1.5 to 4 times faster than Famos and 2 to 6 times faster than LearnHA. So conclusion is that Dainarx can learn a very extensive form of hybrid systems in a very quick manner. And since we have spoken about time, here we have a formal justification of the time complexity of our algorithm. This is the result, but the message is that our complexity is polynomial in the size of the learning data and the size of the target system. For example, D is the learning data. And here, in theory, we have a quadratic time complexity, but this complexity can become really lower in practice, as observed from our experiments. Good. To sum up, we focus on the problem of inferring a nonlinear hybrid automaton from a set of input-output traces of a hybrid system. And the main results we have is first the framework Dainarx, which provides a threshold-free trace segmentation and clustering, all based on the technique of NARX model fitting. And this is the first approach that can give all the different types of the system identification I listed here. And Dainarx exhibits promising performance for inferring diverse complex nonlinear systems. There are many future directions to explore. I will only point out 3 here. So the first is how to obtain good NARX templates, of course. And it would be interesting to explore whether machine learning techniques can help us to learn a good NARX template from the data. Second is whether we can extend Dainarx to some robust hybrid system identification, which actually admits noise or error terms in our systems. And the last but not the least is to establish some quantitative guarantees on how close the learned automata is to the real automata instead of to the data. And we foresee that the PEC learning framework can play a big role here. And for more details, I will welcome you to read our paper titled this, but it's still an under review paper. So if you're really interested, feel free to drop me a message and I will be very happy to share the manuscripts. And if time permits, please allow me to use my last slide to do a little bit advertisement. So I have a freshly established group at Zhejiang University, and we are constantly on the hunt of postdocs, PhDs, masters, research interns in all the aspects of verification, cyber-physical systems, programming languages, and so on. If you're interested or some other collaborations with our group, feel free to drop me a message. Thank you again, and I will be happy to take some questions.
So many thanks, Mingshuai, for a very interesting presentation, and I think you presented plenty of highly interesting aspects. And yeah, I'm also sure there will be several questions. Who wants to start first? Friederike?
Yes, I do have a question, and yeah, maybe it's not the best question, yeah, never mind. I will just ask a question. So what do you consider in your benchmarks as mode switching activity? Or could you give an example for one of these benchmarks, maybe?
Yes, I do have an example. I think here. Let me zoom in a bit. Yes, so this is a so-called Dufin system, which is commonly used in physics. And here I have two modes, a high damping and low damping. And then by a mode switching, basically it means the time point or timestamp at which we switch from, let's say, the high damping mode to the low damping mode. And this timestamp is called mode switching. And how do we identify this? We don't actually. This is only used to illustrate how close we can learn and how precise our approach is. But when you really use our tool, you don't need to provide such mode switching points. It's only for the purpose of testing how close it is. And in our experiments, we do have such mode switching points to evaluate the performance of our tool, and we do this by numerical simulation to get the switching point as precise as possible.
Okay.
I'm not sure whether this answers the question.
Yeah, definitely. And this triggers a follow-up question, because then, as I understood your approach, you want to show or want to evaluate how good the tools you provide still work, even though there might be some switching activity.
Yeah, true.
If it can adjust. Okay. Yeah. Thank you.
Yeah. You're welcome.
Yeah. The next questions, Luc.
Yes, please. Thank you for the talk. So my question is, or for instance, what do you mean exactly by learn? When you say learn, it means that you estimate some parameter or you solve equations? Or what do you mean by learn?
Very good question. By learning, I mean, give me a sec. By learning, I actually mean by finding some valuations of these parameters such that the whole equation well fits the data points. That's simply what you mean, or what you suggested for the word learning.
Okay, so you mean you solve a linear system?
Yes, we always solve a linear programming or linear optimization system, because whenever we do not model fitting, we do this this linear square method, and is in fact a linear optimization problem.
Okay.
This one.
And also, I wanted to know, what do you mean by state? So state is x at time tau minus 1. So it's a vector containing several x, or it's only x? What do you mean by state?
A state is a vector of different variables.
Okay,
you can have x1, x2, and yes, at the same time, t.
At the same time. Okay.
Yes.
Okay. And the last question is also about definition. Is when you speak about agnostic derivative, you mean the derivative of what?
Let me go to the slide. I think I need this slide. Yes, the derivative. The derivative of the state along these traces. That's what I mean by derivative. For example, at this point, if you calculate the first order derivative of the state, you will get something like this, right? The
yes,
slope.
but here you do not see the state. You see some kind of output, because probably
yes,
here
true.
you have a second order system.
Yes, so yeah, that's a good question. So because in learning, we always have discrete data samples. We don't have a continuous traces as state, right? And in approaches like FAMOS, it actually uses a similar sliding window technique to approximate the slope around a certain point. So even though you don't have the continuous trajectory, you can still approximate the slope by, let's say, computing the slope like this. And then farmers will treat this as a approximation of the derivative of the original continuous trace.
Okay. So yes, I understand this,
And
but
yeah,
okay, because here, so when you show this, you mean that the state is theta. You probably mean that the state is theta here. It's not an output, it is a state.
yes.
But
This is
but
the
to,
state.
but to me, the state is not only theta, because you can see that since you have some oscillation, probably you have a second order system. So probably the state would be of order would be of dimension 2, not of dimension 1.
You
Whereas,
are right. Yes. For this specific example, it's a one order first order system. That's why we only have theta here. This is for the specific example. And for different high order systems, we do have
okay,
different orders of vectors, and then all those vectors constitute our state. All right.
okay,
So let me switch to this point.
so,
This would be our state.
okay. Thank you very much. Thank you.
Yeah.
Yeah, I think Luc's question also triggered a follow-up from my side. Because what you have to know here is, let's say, a little bit of information about the internal memory that your system has. What Luc mentioned
Yes.
before is a two-dimensional state. Let's say if it's a mechanical system, you would have position and velocity as the physical state variables. If you have a one-dimensional output variable x in your case, or theta is the output, that means you need at least a second-order difference equation to approximate the dynamics. And how do you tune? What you explained is, you explained that you need some engineering insights at the moment to develop your templates for the NARX modeling derivation. How do you get the insight of the memory length or about the order of your NARX model with respect to time? Is this also engineering insight? Is it gut feeling, or do you have some, let's say, more systematic strategy?
That's a very good question, and so the short answer would be yes. It's also a gut thing. So we do the same engineering perspective thingy. We don't have a good strategy to know in advance what should be the appropriate order of the system. We simply provide some template, and of course you can do in an incremental manner. Say try first order and then increase the order, but no smarter ways to do it for the moment. Yeah.
Okay, but what you would do in reality is maybe you know that's a robotic arm, you have some inertia, the thing that you're measuring are positions, then okay, Newton's
Yeah,
law,
that would be very good.
Lagrangian equations tell you we need to map accelerations, velocity, and positions, therefore at least order 2.
Yeah,
Okay.
I agree. But most of existing approaches do the same heuristic engineering stuff, I would say. Yeah.
Yep. Then the next follow-up question that I have is, your model fitting that you're doing at the moment, with the help of this optimization problem. I think this works quite well if you have data that are not extremely noisy.
True.
What do you
Yes.
do in the case of noisy data? Do you do some pre-processing, some filtering on inputs and outputs? Or do you have some other uncertainty quantification strategy for this?
Currently, we don't have any special treatment for noise. This is why I listed this as one of the future directions. But one way we foresee that can be helpful to tackle noise is that, let me scroll to the slides. It's because of this model itself. So NARX is a widely used model in hybrid system identification. Especially this is suitable to tackle noise. How we can do this is by simply allow an error term, I think somewhere here, say epsilon tau. So you can actually model noise as an internal struct of the NARX model, and then this term will be responsible to take account of noises throughout the feeding process. But this is only a very vague idea that how we can handle this. I would still do this in future, I think, because currently we don't have a very good a strategy for noise data. So all the data we collected are using are obtained using some high precision numerical methods, say range quota, and we don't actually assume noises therein. Yeah.
Because the thing that came to my mind when you presented this, I think it was on the slide, yeah, the fully developed slide 10, when you also had the equations there for the least squares estimate. What you could do is you could also do a set-based least squares estimation. And in the case that you have, for example, guaranteed bounds on measurement uncertainty on your state, what you could then do is you could solve this optimization problem here also with the help of interval arithmetic. If you have uncertainty on X and therefore an interval bound on D, and then you could quantify how critical this uncertainty is when identifying all the values that you have in, yeah, as the coefficients of A1, A2, B1, and so on.
Yeah, I think that would be a very interesting direction to explore because, using intervals as approximations to handle noise is very commonly used. The only concern I have here is whether the intervals would bloat in some sense. So, like inertiality analysis.
This is
I'm not
definitely
so
the
sure,
danger, because what you would have to do there is, I think you don't know in advance correlation of the uncertainty over time. This is unknown. And therefore, for example, if you look at your formulas, if you have your x2 squared, x3 cube, and so on at different points in time, you would have to assume that the uncertainty is totally uncorrelated.
Exactly.
Yes, and this
yes.
definitely leads
yes.
to a phenomenon of the explosion. But
Yeah.
but maybe at least
But I
it could
think
be a
it's,
nice
it's
hint about how sensitive the result is.
yeah, definitely. Yes. Yeah.
Yeah, and the last question two last questions, in fact. One is, at the moment you do the identification offline, but you have shown at the very end that your solver is very quick.
Yes.
Could you be able to use also your solver somehow at runtime to detect whether your system is running into a mode that still does not exist in your model? And such kind of mode could then be a faulty system behavior.
So you mean to
That you're doing some
to,
kind of online monitoring in order to
yes,
detect
online
faults or
monitoring and
failures.
falsification.
Yeah.
I think take it to the online mode. I think it's definitely doable because of the efficiency. But falsification, I have to think about that. What do you mean by the system run into an error mode?
Yeah, for example, you have some faulty system behavior. Sensor and actuator does no longer behave the way it was designed. And offline, with the help of some training data, you already have identified your automaton for the nominal system behavior. You have all the modes that typically occur. And now, due to the fact that something is broken, you run into a mode that you do not have yet in your automaton. And this mode then is representing a faulty system behavior.
Yes, that would be a very nice extension, I think. If this is doable, then our approach actually equipped this system with the possibility to recover from the faulty mode into the normal mode, let's say using our learned model, to make the whole system resilient to some unknown behavior. I think that would be a very nice extension.
Yeah, this could be something like control reconfiguration that you could then do in order to recover. For example, if you have an over-actuated system model, switch off a faulty actuator, switch to something else, maybe lose a little bit of performance, but still you're able to operate your system.
Yes, I agree. Yes, very nice idea. Thank you.
But it
Yeah.
could also include like potential faults that are known, like predefined fault states, so to say, right? If there's a high risk of a sensor failure, that's maybe not the best example, but you know this specific fault could happen, and you already implement some sort of solution strategy for that.
Yeah, I think that's
Yeah,
also a
yeah.
very nice extension because then you would just take the automaton that you have learned and add additional modes that some kind of expert knows as possible faulty scenarios, and then you're just adding them manually, although they were not yet in the training data set.
Yeah. Yeah.
Okay, great. Any further questions?
Do you have any further question, Andres? Because you said 2 last questions.
Yeah, still, you're right. There's one last question that I wanted to ask. At the moment, you assumed that your training data, exactly the slide here, they're more or less homogeneously distributed over the range that is necessary to describe the mode. What do you do if you have sometimes very sparse data at some points, maybe also some data imbalance? Do you have some strategies for this, or is this also an outlook to do some kind of mitigation against imbalanced data?
Yeah. This is I would say this is a difficult question. So currently, it's still in the outlook picture of the work. But speaking of unbalanced data, the only thing I can think of, which is not related to your question perhaps, but we do have such a problem in our guard learning phase where we use SVMs. And there, because the mode switching points are, the number of mode switching points is way less than the number of non-mode switching points. And we have such an unbalanced problem. And there we have some weighting trick to weight different types of samples. But speaking of the learning data itself, no, currently we all have some nicely distributed data, as you said.
Yeah, also for the learning data, I
know,
think the only thing at least that comes to my mind at the moment is ask someone to make a suitable design of experiment to measure the required data that they are nicely distributed, that you can also guarantee identifiability of your different dynamics.
Yeah, but then I said sacrifice a bit of the automation because you always need someone to tell you some knowledge in advance. Yeah.
Okay. This has been my second question. Now, final chance for the other participants to ask any questions. If this is not the case, then thanks again for your presentation. Thanks to the audience for attending the seminar, for asking questions. And yeah, the remaining thing is I wish all of you a nice weekend. And yeah, see you soon in one of the upcoming seminars.
Thank you for your talk.
Bye-bye. Thank you.